Welcome to qnawire.
In this problem, let's see here. We have a power plant, and it is a cogeneration plant with uh, non-ideal pump and turbine. We bleed off some steam here to go to a process heater where we, use some of the heat for something else. Did they actually give us a scenario here? Textile plant. Ah, there we go. So for whatever reason, we have a textile plant and we want some heat for it. Um, so we have steam. High pressure side is 8 megapascals. We bleed off some at 2 megapascals. Low through the condenser is 20 kilopascals. And again, we have inefficient, and these aren't necessarily vertical, but they're obviously very small, so it's hard to even tell what um, if those are vertical or not. Now, let's see here. We know that the mass flow rate through the process heater is 4 kilograms per second, and that through is this? I think that was out of the turbine and leaves enters the turbine at a rate of, yeah, so this is what's coming out of the turbine, and then what's going into the turbine is 11 kilograms per second. All right, so let's get on with the analysis. 20 kilopascals down here, saturated liquid. You can get the pump work, remembering to use the efficiency value, and so we can get the enthalpy at the exit of the pump. We have a saturated liquid at 2 megapascals coming into 3. And then we can do an energy balance on the mixing chamber here. So that gives us, we know everything in here except for H4, so we can find the enthalpy coming out of H4, specific enthalpy that is, which then allows us to figure out what the specific volume at 4 is, because we also know the pressure. And with that specific volume and the pressure change between 4 and 5, we can get the specific work that this pump here does on the steam, or the liquid, the water at this point. So then we can get the enthalpy at the exit of this pump using an energy balance. And again, we got to remember to use the efficiency here when we calculate this. So at 6, we know pressure and temperature. Going into the turbine, we have 500 degrees C. So we can get enthalpy and entropy. At 7, we know pressure, and we know in the isentropic case, we know the entropy. So we can get the isentropic enthalpy, and then using the efficiency of the turbine, we can get the actual enthalpy. At 8, we know the pressure, and we also know we can get the isentropic case, so we can get the isentropic enthalpy at 8. And then we can use the efficiency to get the actual enthalpy at 8. Now we have all of our enthalpy, so and we know all of our mass flow rates, so we can get power or energy flow. So out of the process heater, so we have some, we have some coming out here, and we have out here, and here we have in, oops, and I forgot out at the condenser. Now, obviously, this and this we're using, that we're not using. So we can figure out that just by knowing the difference in enthalpy here. And that winds up being about 8.6 megawatts. Out of the turbine, we can figure out the work out from the turbine by just basically looking at the work done by the flow here and then the flow from here to here. So from here to here, we have 11 kilograms per second, and we know the enthalpy difference. And then from here to here, we have 7 kilograms per second, and we know the enthalpy difference. So we can get the work out of the power out of the turbine, and that's about 8.7 megapascals. The work into the pumps, again, we know the mass flow rate through this one, and we know the mass flow rate through this one. So we know the specific work for each one, so we can add those up, and we get a net of about 95 kilowatts. And so the net, we need to take this, subtract this, so we get about 8.6 megawatts of power net out of this plant. We can figure out the heat transfer in, because we know the difference in enthalpy across the boiler, and that turns out to be about 31.9 megawatts. So the utilization factor, which is just the amount of energy that's flowing out that we're using, divided by the amount of energy that's flowing in, winds up being 53.8%. So we're using this and this, but we're not using this. So that's why this is not 100%.